Welcome into Calculus 3. Today we are going to go over the chain rule. Now it should seem familiar because we talked about the chain rule in Calculus 1 when we were doing derivatives, and we've been using it all throughout this course as well. Right, so just so we know, if we have some function which is y is equal to f of x, where x is also a function of t, right, by the chain rule dy dt is equal to dy dx times dx dt, right? That's the chain rule we learned about in Calculus 1. Now we want to take that same idea and extend it into Calculus 3, right? The difference is, instead of derivatives, we're now going to be dealing with partial derivatives, right? And we're going to break this up into cases. So let's start with what we call case 1. You'll understand the difference in the cases as we go. So the chain rule for partial derivatives or for Calculus 3, let's say I have z, we'll start it up here, is equal to some function f of x comma y. And in this case, right, we're going to say we have both x and y here are functions of t. So we'll say x is going to be equal to g of t. And we'll say y is also going to be some function of t. We'll say h of t. Awesome. Okay. So the chain rule that we're going to use here is if we want to find the derivative of z with respect to t, we're going to say this is going to be equal to the partial derivative of z with respect to x times dx dt. And now we're going to repeat that. We'll add the same thing, but now we need to do it for y. Partial of z with respect to y times dy dt. Now the reason why we're calling this case 1 is because these functions x and y are only functions of t. You're going to see in case 2 it might be s and t and so forth, right? So for case 1, they're both functions of t. Okay, so let's jump straight into an example. So let's say I'm going to give us some function z here. So we'll say z is equal to, let's go ahead and do x y cubed. And we'll say minus, we'll do x squared y. And we'll go ahead and also give you what x is equal to. We'll say x is equal to t squared plus 1. And we'll say y is going to be equal to t squared minus 1. And feel free to pause at any point and proceed on your own. Right, at this point, all we're going to do is just start filling in everything that we need. So let's do the partial derivatives first, right? And that's coming from z. So the partial derivative of z with respect to x is going to be equal to, so x is a variable, y is a constant. We just end up with y cubed here, minus 2xy. We'll do the same thing for now y. So now we'll do the partial of z with respect to y, and this is going to be equal to 3xy squared awesome, minus, again with respect to y, minus x squared. So we have our partial derivatives done, right, which are these two parts here. Right, we have both of these parts done. And now we need to find our dx dt and our dy dt. So we'll do dx dt first, but they're the same thing. If anyone's already calculated ahead, right, dx dt, derivative of x with respect to t, 2t. And we have dy dt, also 2t. Okay? And now we just need to put all of this information together. It's going to be ugly at first. We'll see why. So let's go ahead and start writing this out. We have dz dt is equal to, this is a d, is equal to, we have partial of z with respect to x right here, y cubed minus 2xy times dx dt, which is 2t, plus partial of z which is going to be, with respect to y, which is going to be 3xy squared minus x squared times 2t. Now, unfortunately, right, this looks ugly. Why does it look ugly? Well, we have y's, we have x's, we have t's. Right, now this is asking for what is dz dt. Right, so unfortunately, what do we need to do? We know what x and y are equal to. In terms of t, we're going to need to go make a substitution. Now, this is going to be very long and drawn out, so bear with me. Let's go ahead and write the whole thing just so our answer is complete. I think we did yellow for this one, so let's try green. So we'll say now, dz dt is going to be equal to, instead of y cubed, we have that y is equal to t squared minus 1. Maybe you get where this is going, right? So this is t squared minus 1 cubed minus 2 times x, which is t squared plus 1, times y, which is t squared minus 1. One more parenthesis, all times 2t. So that is our first part, right? Now feel free to simplify that. I'm going to leave it for now. I'll leave it as an exercise if you want to just do some algebra in your spare time. Right, let's go ahead and do the rest. So now we have plus, again, so this was this first piece here. Now we will do the second piece. See if we can fit the whole thing here. So plus, what do we have? 3 times t squared plus 1 times y squared. So we have t squared minus 1 squared. Good. Minus x squared. So minus t squared plus 1 squared. End parenthesis, right? End parenthesis times 2t. So times 2t, and we just did it. Perfect. Right, so obviously we can go through this, simplify, combine like terms. I'm going to leave it for now. I don't want to not waste, but use more video time. I know you can do that on your own. Over here, just so you know, we have this little tree diagram. Now, it doesn't really add too much value for this simple, right, case one where we're both variables of t. But as we move forward, we'll see where this tree diagram will come into play a little bit more. So I'll explain it in the next part of the video. I will see you there. Let's go ahead and jump into case 2. Now, case 2, very similar. Let's go ahead and write out what we're dealing with. Let's say we have some function z, which is f of x, y again, right? So no difference here. But now instead we're going to say our variables x and y are both functions of not only t, but also s. Oh, let's put an h here, yeah? There we go. So we have two functions, right? X and y, both functions of two independent variables. So all that's going to happen here is we're going to have twice as much work, right? So meaning, if I want to find, right, the partial of, let's do z with respect to s, that means I need to do the partial of z with respect to x times the partial of x with respect to s plus the partial of z with respect to y times the partial of y with respect to s. So this is for s, right? Now notice that now that we have two independent variables, we want to make sure we're keeping track of everything. So this is kind of where this tree diagram that we have over here comes into play. Right, so making sure that we keep track of all the variables that we've already used. Now this is for the partial with respect to s. Let's go ahead, we'll write the same one. Partial of z with respect to t now, similar process. We'll write it out, partial of z with respect to x times partial of x with respect to t plus one more time, partial of z with respect to y times the partial of y with respect to t. So quite a few variables that we need to do here. We can underline, of course, there's some repeats, right? So the partial of x here, right? These occur in both of them, right? So we do get to reuse a little bit of information. Let's go ahead and jump into an example, right? So I'll give you some z. Let's say z is equal to e to the x sine of y. And we'll say x is going to be equal to, let's say, st squared. And we'll say y is going to be equal to, let's do s squared t. Awesome. Okay. So let's just make a chart of all of our information that we need. All right, so we'll go down the line here. Let's do partial of z with respect to x. All right, so partial of z with respect to x. What do we have? This is going to be, well, derivative of e to the x stays e to the x, so nothing changes, right? Sine of y. We'll do the same thing, partial of z with respect to y. What do we get? In this case, the sine of y, sine is going to change to cosine, so we just end up with e to the x cosine of y. Right, not too bad. All right, now we need, which one? We can do either one first. We'll do the s's first. So partial of x with respect to s, we'll just do the x's first, right? So x here, with respect to s, we get a t squared. Partial of x with respect to t, what do we get? We get the 2 comes down in front, so 2st. And same idea here, right? We'll do the partial of y with respect to s. What do we get? 2st. And the partial of y with respect to t will be s squared. Awesome. Okay, now we're just going to put it all together, right? So we do have 2 separate answers. Let's go ahead and write these out. So we have the partial of z with respect to x, s. Let's do that one first. What do we have? This is going to be equal to partial of z with respect to x, e to the x sine of y, times partial of x with respect to s, partial of x with respect to s, t squared, plus, now we have partial of z with respect to y. Where's our information? Right here, e to the x cosine of y. Times partial of y with respect to s, 2st. Now I'm going to do this first one for you. I'm going to let you, I'll leave it as an exercise. 1, because you guys should practice on your own. 2, because I'll run out of board space. But we have our partial of z with respect to s here, right? And so, of course, same issue that we ran into last time. We don't want to leave this in x, y's, and t's, or and s's here, right? So we need to change all of this to s's and t's. We know what x is equal to, we know what y is equal to, so all we have to do is make that trade. So let's rewrite this. Below, we'll say the partial of z with respect to s is going to be equal to e to the x. Well, x is equal to st squared, right? So we have e to the st squared sine of y, which is s squared t, times t squared plus, same idea here, e to the x. We have e to the st squared cosine of y, which is s squared t again, times 2st. And we could have reformatted this. Normally we put the 2 at the front, but we'll leave it for right now. Right, so again, repeating pattern. Now we have 2 of these to do. I've done one of them for you. Take a second, fill out the other one. Right, we took the partial with respect to z of s. That means we need a few pieces here. Same thing, partial of z with respect to t, a few pieces there. The best way is to keep track of all of your information, right? That's the tough part. We want to make sure we're using the right partial derivatives. That's why you want to reference the tree diagram over here as well to make sure you have all the correct pieces. Once we solve, right, we're in this process of x's, y's, t's, and s's. We want to be in st land, so make that substitution and you should be good. Feel free to finish the last part of this problem. I'll see if I can post a solution in the comments so you guys can make sure you did it correctly. All right, I'll see you in the final part of the video. All right, let's go ahead and do the last case, which is just known as the general case, right? So you should see it pop up here, a very mathematical definition of what we're about to do, but essentially the more variables that we have, the more partial derivatives we need to do. So let's go ahead, we're just gonna jump into an example. So I'll give you some function, let's just say z is equal to x cubed plus x squared y. And now instead we're going to have functions of x and y, but they're going to be 3 independent variables. So we'll say x is equal to negative s minus t plus u. And we'll say y is going to be equal to, let's just do s t u squared, right? So let's find all of the partial derivatives that we need. So we'll start off with our z. So we'll do the partial derivative of z here with respect to x, and we also need to find the partial of z with respect to y. So let's find both of these. Feel free to pause the video. For this one we have 3x squared plus 2xy. And for this one, this entire thing is a constant, right? So we just end up with x squared, which is nice to work with. We'll switch colors. For our x and y, we need 3 different variables, the partial with respect to s, t, and u, right? So let's go ahead. The partial of x with respect to s, partial of x with respect to t, and the partial of x with respect to u. And these should all be fairly nice, right? Derivative of negative s, negative 1, derivative of negative t, negative 1, derivative of u, positive 1. And our last one here, we need all of our y's, right? So partial derivative of y with respect to s, with respect to t, and with respect to u. So with respect to s, right, we just end up with a t u squared. With respect to t, we just end up with an s u squared. And finally, one interesting one, right, with respect to u, 2s t u. All right, now we have all of our partial derivatives in place. So what are we trying to solve for? We need 3 different ones. I'm going to do 2 for you. I'll leave the last one for you guys to solve, and I'll post the solution in the comments. So we're looking for the partial of z with respect to s, the partial of z with respect to t, and the partial of z with respect to u. So let's do the first one, right? So the first one with respect to s, we need the partial with respect to x first. So we have 3x squared plus 2xy times the partial of x with respect to s, which is negative 1, plus, now we need the partial of y or partial of z with respect to y, x squared, times the partial of y with respect to s, which is tu squared. And per normal, right, we don't want to end up with x's, y's, t's, u's, etc. We want to end up with just either s, t's, or u's, right, or independent variables. So we need to make a couple substitutions. Now this -1 is going to be multiplied in, right, so we're going to end up with -3, and instead of x squared, we're going to write what x is equal to, which is going to be -s minus t plus u squared, minus, right, because this negative sign is going into the 2 as well, minus 2 times another -s minus t plus u times y, which is stu squared. So this is our first piece, right? And let's go ahead, we're going to put this in parentheses. stu squared plus our last piece here is x squared. Again, one more time. -s minus t plus u squared. Oh, plus u, sorry. Squared comes afterwards. X squared. Squared comes afterwards. Pay no attention to that squared. Times tu squared. Awesome, right? So that is our first one. I'll do one more with us. I'm going to save the partial of z with respect to u for you guys. But let's go ahead. We'll do the partial of z with respect to t. Partial of z with respect to t. And what is this going to be equal to? Well, we have the partial of z with respect to x still. Right, so this is all going to be the same, actually. We might even be able to simplify it a little bit earlier. But we'll write it out just so we see it. So partial of z with respect to x, 3x squared plus 2xy times the partial of x with respect to t. Again, this is also going to be a -1. So this first piece is going to be identical plus the partial of y, or partial of z with respect to y. So far it's exactly the same, plus x squared times the partial of y with respect to t now is slightly different, right? su squared. So actually, if we're looking at our above one, it's identical all the way up into this very last piece. Right, so if you're doing your homework, you can copy and paste it, change the last piece, it'll save you a little bit of time. So we have -3, -s minus t plus u squared minus 2 -s minus t plus u times stu squared. Right, all of that is identical from above, as well as this part, right? Plus -s minus t plus u squared on the outside, we'll get it right this time, times, now this is the only part that's different, the su squared. Awesome, right? And again, I'll post the solution to the last one, but hopefully these two helped. So again, we have the 3 different rules. And again, this tree diagram over here should help with this, but we have the 3 different rules, right? We have the basic one, which is just a function which has just one variable. We took it up to case 2, which has 2 variables. And then we have the extended version, which could have n variables, right? So you can imagine if there were more independent variables, this process would keep going. Hopefully these examples helped. If you have any questions, comments, feel free to ask in class or leave them in the comment box. I will see you guys later.